Equilibrium points in n-person games. One may define a concept of an n-person game in which each player has a finite set of pure strategies and in which a definite set of payments to the n players corresponds to each n-tuple of pure strategies, one strategy being taken for each player. For mixed strategies, which are probability distributions over the pure strategies, the payoff functions are the expectations of the players, thus becoming polylinear forms in the probabilities with which the various players play their various pure strategies. Any n-tuple of strategies, one for each player, may be regarded as a point in the product space obtained by multiplying the n strategy spaces of the players. One such n-tuple counters another if the strategy of each player in the countering n-tuple yields the highest obtainable expectation for its player against the n1 strategies of the other players in the countered n-tuple. A self-countering n-tuple is called an equilibrium point. The correspondence of each n-tuple with its set of countering n-tuples gives a one-to-many mapping of the product space into itself. From the definition of countering we see that the set of countering points of a point is convex. By using the continuity of the payoff functions we see that the graph of the mapping is closed. The closedness is equivalent to saying, if P1, P2, and Q1, Q2, Qn, are sequences of points in the product space where Q, P and P, and Qn counters P and then Q counters P. John Forbes Nash Jr. was a brilliant American mathematician whose work in game theory, differential geometry, and partial differential equations fundamentally altered the fields of economics, biology, and military strategy. He is most famous for developing the concept of the Nash equilibrium, a mathematical state in a non-cooperative game where no player can benefit by changing their strategy if the others remain unchanged. Despite his intellectual ascent, Nash struggled for decades with paranoid schizophrenia, a battle that was later popularized by the book and film A Beautiful Mind. His resilience and the enduring impact of his early work eventually led to his receiving the Nobel Memorial Prize in Economic Sciences in 1994, marking a rare and profound bridge between abstract mathematics and the complexities of human behavior. John Forbes Nash Jr. was born on June 13, 1928, in Bluefield, West Virginia, into a household that valued intellectual pursuit. His father was an electrical engineer and his mother a former schoolteacher. As a child, Nash was notably solitary and introverted, often preferring the company of books such as Compton's Pictured Encyclopedia and E.T. Bell's Men of Mathematics over playing with other children. Although he wasn't always a straight-A student in the traditional sense, his mathematical talent was undeniable. By high school, he was already taking advanced courses at a local community college and solving complex proofs in ways that often bypassed his teachers' more clunky methods. He eventually earned a full scholarship to the Carnegie Institute of Technology, now Carnegie Mellon, where he initially struggled to find his footing in chemical engineering and chemistry before realizing his true calling was mathematics. His rapid ascent in the field led him to Princeton University for graduate school in 1948. It was there that his advisor, Richard Duffin, wrote what is perhaps the most famous letter of recommendation in academic history, containing just one sentence: "This man is a genius." Prior to his groundbreaking mathematical career, Nash published an applied engineering paper while still an undergraduate. In 1945, his work sag and tension calculations for cable and wire spans using catenary formulas appeared in the Transactions of the American Institute of Electrical Engineers. This technical paper demonstrates his early aptitude for solving complex practical problems using mathematical modeling, focusing on the precise physics of suspended cables long before he turned his attention to abstract game theory and geometry. Equilibrium points in n-person games 1950. This one-page note, published in the Proceedings of the National Academy of Sciences, contains one of the most consequential ideas in the social sciences. In it, Nash introduced the concept that would forever bear his name, the Nash equilibrium. With elegant brevity, he defined an equilibrium point as a profile of strategies, one for each player, where no individual can unilaterally deviate and improve their payoff. Using the Kakutani fixed point theorem, he provided the existence proof, demonstrating that every finite n-person game possesses at least one such equilibrium in mixed strategies. This deceptively simple paper provided the missing cornerstone for a rigorous theory of strategic interaction, transforming economics, political science, and evolutionary biology by offering a universal tool to predict stable outcomes in conflict and cooperation. The Bargaining Problem, 1950. Published in Econometrica, this paper tackled cooperative game theory by providing the first rigorous, axiomatic solution to the two-person bargaining problem. Nash shifted the focus from psychological haggling to a mathematical formulation. He proposed a set of seemingly reasonable axioms including efficiency, symmetry, scale invariance, and independence of irrelevant alternatives, and proved that only one solution satisfies them all. This solution, the Nash bargaining solution, selects the outcome that maximizes the product of the player's gains over a disagreement point. It provided a powerful and clean predictive tool for situations where binding agreements are possible, establishing a foundational framework for analyzing negotiation, arbitration, and fair division that remains a central pillar of microeconomic theory. Non-cooperative games, 1951. This paper, published in the Annals of Mathematics, is the formal expansion of Nash's PhD dissertation and the definitive mathematical treatment of his equilibrium concept. It moves beyond the concise existence proof of his 1950 note to establish the full architectural framework for non-cooperative game theory. Here, Nash rigorously defined games in extensive and normal forms, formalized the concepts of mixed strategies and expected utility, and provided an alternative, more accessible existence proof using the Brouwer fixed-point theorem. The paper firmly established non-cooperative game theory as a distinct and vital field of mathematics, providing the language and formal machinery that would enable decades of subsequent research in economics, computer science, and strategic decision-making. See Superscript 1 Isometric Embeddings, 1954. In this landmark paper, Nash provided the first major breakthrough in solving the isometric embedding problem, a fundamental question in differential geometry dating back to Riemann. He proved that any compact Riemannian manifold of class Ck for k greater than or equal to 3 could be isometrically embedded into a Euclidean space of sufficiently high dimension. This result was surprising and powerful, demonstrating that abstract geometric spaces could be realized concretely within ordinary Euclidean geometry. The proof was a triumph of ingenuity, employing a sophisticated hard implicit function theorem and a novel iteration scheme that became known as the Nash-Moser technique, later refined by Jürgen Moser. This paper established Nash as a world-class geometer. The Embedding Problem for Riemannian Manifolds, 1956. Building on his 1954 breakthrough, Nash vastly strengthened and generalized his embedding theorem in this longer, more comprehensive work. He achieved two monumental improvements. He removed the compactness assumption, proving the theorem for any Riemannian manifold, and he dramatically reduced the required dimension of the embedding space, showing it depended primarily on the dimension of the manifold itself rather than being arbitrarily large. This paper solidified his solution to one of geometry's most profound questions, proving that the local, intrinsic curvature defined by a Riemannian metric could always be faithfully represented in a flat, ambient space. The techniques developed, particularly his intricate smoothing processes, remain deeply influential in geometric analysis. Continuity of solutions of parabolic and elliptic equations, 1958. Shifting fields with characteristic brilliance, Nash solved a central problem in the theory of partial differential equations PDEs. Hilbert's 19th problem concerned the analytic regularity of solutions to elliptic PDEs arising from calculus of variations. Nash proved that solutions to a broad class of nonlinear parabolic and elliptic equations are Holder continuous, a crucial step toward establishing their smoothness. This result, obtained independently and simultaneously by Ennio de Giorgi for the elliptic case, is now celebrated as the Nash-de Giorgi theorem. Nash's approach, introducing novel estimates and a clever use of logarithmic convexity, was radically different from de Giorgi's and provided deep insights into the diffusion of information in parabolic equations. It stands as one of the most celebrated achievements in 20th century analysis. 1959 Early 1990s, period of illness and linguistic philosophical writings. Following the onset of severe paranoid schizophrenia around 1959, Nash's academic output ceased, but he produced extensive, unpublished manuscripts of a linguistic and philosophical nature. These writings, composed during his decades of illness, were characterized by delusional systems seeking hidden codes and cosmic meanings. He filled notebooks with theories of numerology applied to language, attempts to decrypt messages from newspapers like the New York Times, and elaborate cosmological systems where mathematical patterns governed linguistics and prophecy. Notable among these unpublished works is AI vs MI. Artificial Intelligence versus Mathematical Intelligence, which explored consciousness and symbolic communication. These writings reflect his mind's continued, if fractured, engagement with pattern recognition. 1990s to 2015, recovery, recognition, and later refinements. After a gradual recovery in the late 1980s, Nash returned to academic work. His 1994 Nobel Prize in Economic Sciences reignited public and scholarly interest in his early game theory. He began refining and extending his ideas, notably developing his ideal money theory articulated in lectures and a 2002 technical report, which argued for an apolitical, inflation-resistant currency standard and contained elements analyzing money as a linguistic system of value communication. He gave lectures reflecting on his earlier work and his experiences, including commentary on his linguistic theories, now framed more as philosophical musings on pattern and meaning. He also engaged with developments in evolutionary game theory and agent-based modeling until his death in 2015. I spent times of the order of 5 to 8 months in hospitals in New Jersey, always on an involuntary basis and always attempting a legal argument for release. And it did happen that when I had been long enough hospitalized that I would finally renounce my delusional hypotheses and revert to thinking of myself as a human of more conventional circumstances and return to mathematical research. In these interludes of, as it were, enforced rationality, I did succeed in doing some respectable mathematical research. Thus there came about the research for les problèmes de Cauchy pour les equations différentielles d'un flux général, the idea that Professor Hisukiro Naka called the Nash blowing up transformation, and those of arc structure of singularities and analyticity of solutions of implicit function problems with analytic data. But after my return to the dream-like delusional hypotheses in the later 60 seconds, I became a person of delusionally influenced thinking but of relatively moderate behavior and thus tended to avoid hospitalization and the direct attention of psychiatrists. Thus further time passed. Then gradually I began to intellectually reject some of the delusionally influenced lines of thinking which had been characteristic of my orientation. This began, most recognizably, with the rejection of politically oriented thinking as essentially a hopeless waste of intellectual effort. So at the present time I seem to be thinking rationally again in the style that is characteristic of scientists. 9. References: Grigoryan, Alexander 2009. Heat kernel and analysis on manifolds. AMSIP Studies in Advanced Mathematics. Volume 47. Providence, Rhode Island, American Mathematical Society. doi 10.1090 AMSIP 047. ISBN 978-0821849354. MR256, 9498. Kigami, June 2001. Analysis on Fractals. Cambridge Tracks in Mathematics. Volume 143. Cambridge, Cambridge University Press. ISBN 052-179-3211. MR184-0042. Leap, Elliot H. Loss, Michael 2001. Analysis. Graduate Studies in Mathematics. Volume 14, Second edition of 1997, Original ed. Providence, Rhode Island, American Mathematical Society. ISBN 082-182-7839. MR181-7225. Gilbarg, David, Trudinger, Neil S. 2001. Elliptic Partial Differential Equations of Second Order. Classics in Mathematics, reprint of the Second ed. Berlin, Springer Verlag. doi 10.1079-3-642-61798-0. ISBN 354-041-1607. MR181-4364. Lieberman, Gary M. 1996. Second-order parabolic differential equations. River Edge, New Jersey, World Scientific Publishing Co. Incorporated. doi 10.1142 3302. ISBN 981022883X. MR146-5184. Fabs, E.B. Stroke, D.W. 1986. A New Proof of Moser's Parabolic Harnack Inequality Using the Old Ideas of Nash. Archive for Rational Mechanics and Analysis. 96-4, 327-338. Bibcode 1986 ARRMA.96.327F. doi 10.1007 BF00251802. MR085-5753. S2 SID 189774501.